Let us look at the next problem here. It is given that ABCD is a square of 2 meters, charges of 5 nanocoulomb plus 10 nanocoulomb and minus 5 nanocoulomb are placed at corners A, B, C respectively. And we are asked to find what is the work done in transferring a charge of 5 microcoulomb from point D to point of intersection of diagonals. Okay, so this is one of regularly asked questions here, and this question is asked in the year of July 2015. Okay, now let us turn figure given. We have a square of side ABCD is a square here, and charges are 5 nanocoulomb. Let me write it as Q1 is equal to what? 5 nanocoulomb. Q2 is equal to 10 nanocoulomb. Let us write them in sequence. We have Q3 is equal to what? Minus of 5 nanocoulomb. Okay, and let us join the diagonals here, and let me call the point of intersection of the diagonals as O. Okay, then we are asked to find out what is the work done in transferring a charge of 5 microcoulomb from point D to O. Here only these three charges are my source charges. This is test charge. This test charge I will move from point D to point O. Okay. So for finding that work done, first we have to find out what is the potential difference between point D and point O because of these source charges. Okay. Let us consider BD is potential at point D because of charge Q1, Q2 and Q3. Similarly, let me write VO. VO is potential at point O because of the source charges Q1, Q2 and Q3. Okay. First separately we shall find the value of VD, and then we shall find the value of VO. Then we shall find out what is the potential difference between those 2 points, and the work done is given by the potential difference between these 2 charges and the magnitude of the test charge that we are moving. Product of those 2 magnitudes will give me the work done. Okay. First we shall find out what is electric potential. Potential at D. Potential at D because of these source charges, and the side length is given to be how much? 2 meters. All sides are equal to 2 meters. Okay. And if I calculate the value of EC, it comes somewhere around 2.82. Okay. So this A to O is 1.41 meters. All the values of A to O, B to O, C to O and D to O all will be equal to DO, that is equal to CO, that is equal to DO. This will be equal to what? 1.41 meters. For calculations, let us use that value. Okay. Then potential at D, so that I can write it as VD is equal to what? It is the sum of potential at D because of charge Q1. So that we write it as VDA plus potential at D because of charge at B. That I write it as VDB. Okay. Similarly, let me write the potential at D because of source charge C. So that I write it as VDC. Okay. For all these values, 1 by 4 pi epsilon naught is constant. So that I can write it outside here. I can write it as, or separately let me write the values of VDA, VDB and VDC. So this is equal to 1 by 4 pi epsilon naught. For VDA, the source charge is Q1, is it not? And the distance between A and D is how much? That is 2 meters. Okay. So that I write it as, what is the source charge magnitude? 5 into, first let me write the charge value here, Q1 divided by ED. Q1 divided by ED plus what is VDB? It is the potential at D because of charge at B, that is Q2. That I can write it as 1 by 4 pi epsilon naught. Second charge is what? Q2 divided by what is the distance between these 2 charges? That is nothing but that is VD. Okay. Similarly, the equation for VDC is potential at D because of source charge Q3 at C, that is equal to 1 by 4 pi epsilon naught. What is that charge? Q3 divided by what What is the distance? That is nothing but CD. Okay. In this I can take 1 by 4 pi epsilon naught outside. 1 by 4 pi epsilon naught I take it outside. Let me substitute the values. All values are in nanocoulombs, so I can take 10 to the power minus 9 also outside. Yes, into 10 to the power of minus 9. This I can write as 9 into 10 to the power of 9. 1 by 4 pi epsilon naught value substituting here. 10 to the power minus 9 is associated with all the charges. Inside I will just write the numerical values. Here will be 5 divided by 80 is how much? 2 meters. Okay. Plus here I have 10 nanocoulombs. So nano I have taken it outside. So here I have only 10 here. And what is this distance? This is 2.8. Okay. And this source charge is positive. This source charge is also positive. Hence my potentials are also positive. But look at the third charge here. Third charge is negative. Hence the potential because of this negative charge at point D will also be negative. So I write minus here. Okay, by the same convention I write minus. What is the magnitude of the charge? 5 nanocoulomb. 10 to the power minus 9 I have written outside, divided by CD is how much? Again it is 2 meters. Okay, and if I calculate this value I get VD is equal to 63.64 volts. Okay, it is the net potential at point D because of the source charges Q1, Q2 and Q3. Okay, now similarly we shall find out what is the net electric potential at the intersection of the diagonals, that is point O, because of charges Q1, Q2 and Q3. So let me write that as VO. VO is electric potential at O. Directly let me write the values here. So here I can write, so VOA is equal to VOA plus of VOB plus of VOC. Yes, only the charges will remain same, only the distance may change here. Right? So just be careful with the distance here. Here I can directly write 1 by 4 pi epsilon naught, 1 by 4 pi epsilon naught, or I can write 9 into 10 to the power of 9 into 10 to the power of minus 9. Just compare with previous case here, just write the values. Okay. So here my source charge is at E and point of concentration is at O. Here the distance I have to write is what? 5 divided by what is the distance between the source charge and the point of concentration? That is 1.41. Okay, plus second source charge is at B and the point of concentration is O here. The distance here also is same. So here I get 10 divided by the magnitude of the source charge is 10 nanocoulomb. 10 to the power minus 9 I have written it outside already, divided by here I write 1.41. Okay, and similarly the third charge is what? Minus of 5 nanocoulomb. This will be minus here, minus 5 divided by the distance is remaining same, 1.4. Okay, and if I calculate this value I get the value of potential at O as 31.82 volts. Okay, so I have two potentials, one at point D. At point D I have potential of VD is equal to 63.64 volt, and at point O I have VO is equal to 31.82 volts. Okay, and the work done in moving the charge of 5 microcoulomb from point D to O is given by W is equal to potential difference between point D and O into magnitude of the charge that has to be moved. So that is equal to potential difference is given by 63.64 minus of 31.82 into what is the magnitude of the charge? 5 into 10 to the power of minus 6. Yes. So that is equal to what? 31.82 into 5 into 10 to the power of minus 6, which is what? W is equal to 159.1 into 10 to the power of minus 6 joules. Here we need not do any external work. The charge is moved from higher potential to lower potential. The charge moves itself because of this potential difference. Here we have 63.64 volt. Here the charge, the potential is 31.82. The charge moves because of this potential difference from higher potential to lower potential. That work done on the charge is equal to 159.1 into 10 to the power of minus 6 6 joules. Okay, this is the solution for a given problem. Let us look at the next problem here. This question is asked in 2014. They have given that in a parallel plate capacitor with air between the plates, each plate having an area of 6 into 10 to the power of minus 3 meters square, and the distance between the plates is what? 3 millimeters. And we are asked to calculate the capacitance of the capacitor if the capacitor is connected to 100 volt supply. Okay, and they are also asked to find what is charge on each plate of the capacitor. Let us write out the data given. The area of the plates is what? Capital A is equal to 6 into 10 to the power of minus 3 meters square. Yes, and there is air between the plates, and the distance between the plates is what? B is equal to 3 millimeters. This is calculated as 0.003 meters. Yes, then the external voltage is equal to what? That is 100. Okay, direct question they asked. First, we shall find out what is capacitance of the capacitor. We have the equation for capacitance. C is equal to epsilon naught A divided by D. Okay, and let me substitute the value of epsilon naught 8.854 into 10 to the power of minus 12 into what is the area given? That is 6 into 10 to the power of minus 3 divided by distance is equal to what? We shall substitute it in terms of meters. That's equal to 0.003 meters. If I calculate the value, I get it as 17.7 into 10 to the power of minus 12 farads. Okay, this is the value of capacitance of the capacitor. Then we have to find the charge. Very simple question. I can write Q is equal to C into V. That is C just now we have calculated. That is 17.7 into 10 to the power of minus 12 into voltage is equal to what? 100. Okay, so this I get as 17.7 into 10 to the power of minus 10. Right? So this I can write it as 1.77 into 10 to the power of minus 9 volts. Q is equal to 1.77 nanovolts. Okay, this is the value of the charge stored in each plate of the capacitor. Okay, let us look at the next problem. This is one of our regularly answered questions. Let us look at our next problem here. This is one of our regularly answered questions. They have given that when two charges are connected in a series combination across a 4 kilovolt line, the energy stored in the system is 8 joules. Okay, and when the same capacitors are connected in parallel combination across our same line, the energy stored is how much? 36 joules. Okay, find out individual capacitors. Okay, so here there are two combinations. First, we have two capacitors. When they are connected in series, let us consider two capacitors C1 and C2. When they are connected in series across the voltage of 4 kilovolt, that is 4000 volt, the energy stored in the combination. So that is energy stored in the series combination. Let me call it as ES. Let it be equal to how much? 8 joules. Okay. Similarly, when the same capacitors are connected in parallel combination, let me take C1 and C2. When the same capacitors are connected in parallel combination across the same voltage of 4000 volt, the energy stored in the system is equal to what? 36 joules. Okay, because whenever the combination of the capacitors changes, the effective capacitance also changes. Hence, energy stored in the system also changes. Okay, and we know, first we shall write the data given. C1, C2 we have to find out. Yes, voltage is equal to what? Voltage is equal to 4 kilovolt, that I get 4000 volt. Okay, and energy stored in the series combination, that is ES is equal to 8 joules, and the energy stored in the parallel combination is equal to what? 36 joules. Okay, and I have the basic equation for energy stored in the capacitor. Let us consider the effective capacitance of this series combination as, let me write this as CS. Okay, let me write the effective combination capacitance of a parallel combination. Let me write it as Cp here. Okay, the energy stored in the series combination of the capacitors that is given by Vs is equal to 1 by 2 into Cs into V square. General equation is equal to what? E is equal to half Cv square. Here I have combination of two capacitors in series, so I have to consider the effective capacitance of the combination, that I write it as 1 by 2 Cs into V square. By this I know the value of Es. If I substitute it as 8 joules, that is equal to 1 by 2 into Cs into V is given to be how much? 4000. Yes, 4000 square. By this I can write the effective value of capacitance in series combination is equal to, I get it as 1 into 10 to the power of minus 6 farads. So this is the effective capacitance of series combination. Similarly, let us consider the energy stored in the parallel combination of the capacitors. If I write the values, I can write EP is equal to EP is equal to 1 by 2 into Cp into V square. In both cases, the supply voltage is same, and let me substitute the value here. The parallel combination energy stored is equal to what? 36. 36 is equal to 1 by 2 into Cp into V is how much? 4000 square. If I calculate the value, I get the value of Cp as Cp is equal to 4.5 into 10 to the power of minus 6 farads. So this is the value of effective capacitance in series and parallel combination. Okay, then we have the parallel combination is given by what? For parallel combination, Cp is equal to C1 plus of C2. So C1 plus C2 is equal to what? 4.5 into 10 to the power of minus 6 farads. Okay, C1 plus C2 is equal to 4.5 microfarad, and the equation for effective capacitance in series combination is given by 1 by Cs is equal to 1 by C1 plus 1 by C2. This also I get it as Cs is equal to C1 C2 divided by C1 plus of C2. Okay, and this is equal to Cs. Yes, Cs is equal to what? 1 into 10 to the power of minus 6. By this I can write C1 into C2 is equal to 1 into 10 to the power of minus 6 into C1 plus C2 I take to the right side. So if I write to the right side, I get it as 4.5 into 10 to the power of minus 6. So this will give me C1 into C2 is equal to what? 4.5 into 10 to the power of minus 12 farads. Yes, so this is the value of C1 into C2. Okay, then I have two values here. C1 plus C2 is equal to 4.5 into 10 to the power of minus 6. Yes, and C1 into C2 is equal to what? 4.5 into 10 to the power of minus 12 farads. Using these two, I have to find the separate values of C1 and C2. Okay, and we have the identity, that is A plus B whole square minus of A minus B whole square is equal to what? 4 times of ET. Okay, here also I have C1 and C2 in place of A and B. By using this identity, I can write C1 plus C2 whole square, C1 plus C2 whole square minus of C1 minus C2 whole square is equal to what? 4 into C1 into C2. Okay, so here I know the value of C1 plus C2 and I know the value of C1 into C2. I can easily find the value of C1 minus of C2 whole square. Hence I can find the value of C1 minus of C2. So I can write this as C1 minus C2 whole square is equal to C1 plus C2 whole square. This I take it to the left side. So this is equal to what? 4 into C1 into C2. Okay, if I substitute the value here, C1 plus C2 is equal to what? That is 4.5 into 10 to the power of minus 6 whole square minus 4 into, what is the value of C1 into C2? That is 4.5 into 10 to the power of minus 12. Okay, this is ultimate C1 minus of C2 whole square. If I calculate and simplify this, I get the value of C1 minus C2 is equal to 1.5 into 10 to the power of minus 6 farads. Okay, so that is the value of C1 minus of C2. Yes, then now I have the value of C1 plus of C2 as well as of C1 minus of C2. Using both identities, easily I can find the value of C1 and C2. C1 plus C2 is equal to what? Yes. C1 plus C2 is equal to 4.58 to the power of minus 6. And I have C1 minus C2 is equal to what? 1.52 to the power of minus 6. Simplify this. I get 2C1 is equal to 6 into 10 to the power of minus 6. This implies C1 is equal to 3 into 10 to the power of minus 6 farad. And if I substitute it in first or second equation, I get C2 is equal to what? 1.5 into 10 to the power of minus 6 farad. So these are the values of capacitances of individual capacitor. Next we have problem based on common potential. Yes, they are given a capacitor has capacitance of 10 microfarad and is charged to the potential of 200 volt. Okay, and the second capacitor having capacitance of 20 microfarad and it is charged to the potential of 300 volt. Okay, and if after charging the two capacitors are disconnected from the battery and they are connected in parallel, what is the energy dissipated? While discussing the concept of common potential, we have seen one capacitor will be connected to first battery and that will be stored to the maximum potential, and second capacitor is maybe connected to another battery that is also stored to the maximum potential here. So like that, here the capacitance of the first capacitor is equal to what? 10 microfarad. Okay, and it is charged to the potential of V1. It is equal to what? 200 volt. And similarly, the second capacitor, which is having capacitance of 20 microfarad, it is connected to the voltage of how much? 300 volt. Yes. And after connecting, we have to find out what is the energy dissipated. Okay. So before the combination, before the parallel combination, there is some energy stored in the first capacitor. Okay. So that energy stored in the first capacitor that I write as V1 is equal to 1 by 2 into C1 into V1 square. Yes. So that is equal to how much? 1 by 2 into C1 is how much? 10 into 10 to the power of minus 6 into V1. V1 is equal to what? 200 square. Okay. Similarly, the energy stored in the second capacitor, let me write it as E2. E2 is equal to 1 by 2 into C2 into V2 square. That is equal to 1 by 2 into C2 is how much? 20 microfarad. That is 20 into 10 to the power minus 6 into V2 square. That is 300 square. Okay. And before the combination, the net energy of the system is equal to what? E is equal to E1 plus of E2. Okay. So that is equal to 1 by 2 into 1 by 2 into, here I can write it as 10 into 10 to the power minus 6 into 200 square plus 1 by 2 into 20 into 10 to the power minus 6 into 300 square. Okay. If I simplify this, I get it as E is equal to 1.1 joule. This is the energy stored in the system of these two capacitors when both are not connected in parallel. Okay. After the parallel combination, here this is the system of capacitors. So here I have C1 is equal to what? Here I have C1 and here I have C2 here. When they are connected in parallel combination, there is redistribution of the charges and until both the capacitors get a common electric potential. Okay, and we know the common potential is known by what? VC is equal to total charge divided by total capacitance of the combination. Okay, so Q1 is equal to what? Q1 is equal to C1 V1 plus of C2 V2. Okay, the charge remains conserved either before the combination or after the combination. So this I can write it as C1 V1 plus C2 V2. And effective capacitance when they are connected in parallel is equal to what? C1 plus of C2. When I substitute the values of C1 V1, C2 V2, I get VC is equal to C1 is equal to what? 10 microfarad, 10 into 10 to the power of minus 6 into V1. V1 is equal to what? 200. Yes, plus C2 is what? 20 microfarad, that is 20 into 10 to the power minus 6 into V2 is 300 volt. 4 divided by, I have tried C1 plus of C2, that is 10 into 10 to the power of minus 6 plus of 20 into 10 to the power of minus 6. Okay. After solving this, I get the value of DC is equal to 266.7 volt. Okay. So this is the common potential across both C1 as well as C2. At this point of time, the flow of charges from one capacitor to another capacitor stops. Okay. And after the combination, the energy stored in the combination is given by E is equal to 1 by 2 into the effective capacitance is equal to what? Cp into what is the potential, common potential you have to consider, that is of Vc squared. Okay. So E is equal to 1 by 2 into Cp is equal to what? C1 plus of C2, that is 10 plus 20 microfarad, that is 30 into 10 to the power of minus 6. Okay, I have to write C1 plus of C2 into Vc is equal to what? 266.7 square. And if I substitute this value, so this I get it as 1.067 joules. Okay, and the energy before the combination is 1.1 joules. The energy after the combination is what? 1.067 joules. So there is loss of energy when there is transfer of the charges from a higher potential capacitor to lower potential capacitor. Hence there is loss of energy. The loss of energy is equal to what? That is E minus of that is equal to 1.1 minus of 1.067. So delta E is equal to 0.033 joules. Okay. So this is the value of dissipated energy when the capacitors are connected in a parallel combination. Okay. The next problem is given on a combination of the capacitors. They have given that obtain equivalent capacitance of the network shown in the figure, and for 300 volt supply determine the charge and voltage across each capacitor. Okay. This is the network given in the problem. Yes, here we have three capacitors of capacitances 100 picofarad, 200, 200 and 100 picofarads. Okay, let us name these capacitors. So let us call this as C1, let this be C2, this is C3 and this is C4. Okay, we have four capacitors here. The same thing I have just redrawn it. Okay, you can just open this here, you can just open, this is positive terminal, the same thing I have redrawn it here. So here I have only one capacitor, that is the C4. Okay, so this capacitor is what? C4, and C4 is connected to the positive terminal of the supply. Here also I am connecting the C4 to the positive terminal of 300 volt supply. Okay, and combination of these capacitor, that combination, this junction, this corner is connected to the negative supply here. So this terminal I am connecting it to the negative terminal of the battery of 300 volt. Okay, now we can clearly observe here. So this we can name it as A, and let us call this as B, so that it is easy to solve the numerical. Okay, so here this 200 picofarad, this is again C1, this capacitor is what? C2, and this is C3. Okay, here we can observe C2 and C3, they are in a series combination. Okay, and the combination of C2 and C3, let us call it as C23, that is this combination is in parallel combination with C1. Okay, so this combination of C2 and C3, that I call it as C23, that is in parallel connection with C1. Then the combination of all these three capacitors, that is in series combination with C4. Okay, we shall solve it step by step here. First what we shall do, let us find the equivalent capacitance of these two capacitors, that I call it as C23. Okay, so let me draw it again here. So here I have the capacitor of capacitor C4. Yes, then I have capacitor of capacitance 100 picofarad. Let us combine these two. So this I call it as C23. Okay, you can write any name here, and it is just combination of C2 and C3, so I am writing it as C23. And then this combination is connected to again 300 volt supply. Okay, then what is the value of this combination of C2 and C3? They are in series combination. I can write C23 is equal to C2 into C3 divided by C2 plus of C3. When I have only two capacitors in series, I can directly use this formula, and by substituting this I can get it as 200 into 200 picofarad divided by C2 plus of C3. So here I get it as 40,000 divided by 400. So this will be equal to what? 100 picofarad. The effective capacitance is equal to 100 picofarad. So C23 I can write it as 100 picofarad. Okay, and again from the given data, C1, this is C1, so this is also equal to what? 100 picofarad, and C4 is equal to 100 picofarad. Okay, just I have combined C2 and C3. Then let us consider the parallel combination of C1 and C23. These are in parallel combination. I can simply add the values of capacitances here. So this I can write it as, I will redraw it again here. So this is 100 picofarad, that is C4. These two are in parallel combination. I will just add them. So this will be 100 plus of 100, that is equal to 200 picofarad. Yes, again this combination is connected to the external supply voltage of 300 volt. Okay, then these two are in a series combination. The effective capacitance, this I call it as a C123. Okay, so this is the effective combination of C1 and C23. I will write it as a C123. Yes, then to find the effective capacitance, that will be the net effective capacitance of the total combination. Again I will use the formula C4 into C123 divided by C4 plus of C123. I can write C is equal to, let me write, C is the effective capacitance of this network. C is equal to what? C4 into C123 whole divided by C4 plus of C123. Okay, so that is equal to what? 100 into 200 divided by 100 plus of 200, that is somewhere around 66.7 picofarad. I get 20,000 divided by 300, that will give me the value of 66.7 picofarad, or I can write it as 200 divided by 3 picofarad. Okay, this is the net effective capacitance of the network given. Okay, then we have to find out what is the charge stored in each capacitor, as well as what is the potential drop across each capacitor. Yes, so for that let us go reverse here. Then so the final capacitance is, final figure I can draw it as, so this is the value of capacitance, effective capacitance, this is the supply voltage. Okay, so this is the equivalent circuit of a given network. Okay, and what is the value of C here? This is equal to 200 divided by 3 picofarad. So this I have written it as a C, and what is the voltage given? That is a 300 volt. Okay, first before finding out charges in each capacitor, first we shall find out what is the net charge in the system. So here let me write it as Q. Okay, so here Q is equal to what? Q is equal to effective capacitance, and whenever I have only one capacitor here, the supply voltage will be equal to the potential drop across the capacitance. So here also I will have voltage of 300 volt. Okay, I can write this as Q is equal to what? C into V. If I substitute the values, I get Q is equal to, C is equal to what? 200 divided by 3 into 10 to the power of minus 12. They have given it is picofarad. Pico is nothing but 10 to the power of minus 12 into what is the voltage here? That is 300. Okay, so this I get it as 20,000 into 10 to the power of minus 12. This I can also write it as 20 nanocoulomb. Okay, the charge stored in the system is equal to what? 20 nanocoulomb. Okay, now we shall go in a reverse manner here. Here these two charges are in series combination. When the combination is series combination, the charge stored in each capacitor will be equal to the charge stored in effective network here. Okay, so here also the charge stored will be same. So Q, here also I will have the value of Q here. Here also I will have the value of Q, that is equal to 20 nanocoulomb. In both capacitors, same charge of 20 nanocoulomb will be stored. Okay, now in this factor, so this is, so here actually this is point A. Okay, this I had written as point A, point B. So this is also point A. So this is point B here. This is the effective capacitance of these two capacitors. So this is point A, this is point B. Okay, the total charge stored in this parallel combination is equal to what? 20 nanocoulombs. Okay, when it is 20 nanocoulombs, some charge will be stored in C1 and remaining charge will be stored in C23. Yes, but when I observe the capacitance are same here, and to find the charge across this C1 and C23, first let us find what is voltage across this capacitor. Okay, the total supply voltage is equal to what? 300 volt. Okay, so there will be potential drop across C4, that I call it as a V4, and the potential drop across C123, that I call it as a V123. Okay, and this voltage V4 is given by, consider the capacitor C4. From capacitor C4 I can write, from capacitor C4 I can write Q is equal to what? C4 into V4. This implies V4 is equal to what? Q divided by C4. Okay, Q is equal to what? Q is equal to 20 nanocoulombs, that is 20 into 10 to the power of minus 9, divided by what is C4 here? C4 is equal to 100 picofarad. 100 picofarad. This comes out to be V4 is equal to what? This I can write it as 100 into 10 to the power of minus 12. 20 divided by 100, that is 0.2. 1 by 5 I can write 0.2 into this, I take it to the numerator, this will be equal to what? 10 to the power 2. So this implies V4 is equal to what? 200 volt. Out of the given 300 volt, 200 volt is dropped across V4. Okay, so here the voltage is equal to what? 200 volt, and the remaining voltage will be dropped across C123. So this V123 will be equal to what? 100 volt. So that the total voltage in the series combination is equal to what? 200 plus of 100, that is equal to 300 volt. So from this I can write V4 is equal to 200 volt and V123 is equal to what? 100 volt. Okay, and this whatever voltage is there, that will be same across. So between these 2 points, the voltage is equal to what? 100 volt. So here also I will have the voltage of 100 volt. Here also I will have voltage of 100 volt. Okay, so I have same voltage across these 2 capacitors. Then if I consider the charge stored in the C1, yes, the charge stored in the C1 is equal to what? That I can write it as Q1 is equal to what? C1 into V1. Okay, C1 is equal to what? 100 picofarad, 100 into 10 to the power of minus 12 into what is the voltage across that? That is equal to 100 volt. Okay, so I will get Q1 is equal to 10 to the power minus 10,000 into 10 to the power of minus 12. This I can write it as 10 into 10 to the power of minus 3 minus 9 coulombs. Okay, Q1 is equal to 10 nanocoulombs. Q1 is equal to what? 10 nanocoulombs. And similarly, by considering second capacitor C23 also, I can write Q23 is equal to C23 into V23. So that is also equal to what? 10 nanocoulomb. Okay, or we can also do one thing here. The charge stored in the combination is equal to what? 20 nanocoulombs. Okay, and you can observe here the capacitance is 100 picofarad, here the capacitance is 100 picofarad. So equal charges will be shared between these 2 capacitors. So directly I can write the charge on capacitor C1 is 220 divided by 2, that is 10 nanocoulomb, and the remaining charge will be stored in C23. So that is also equal to what? 10 nanocoulomb, or by calculation also we have got the value of Q1 as well as Q23. So the charge stored in the capacitor C1 is equal to what? 10 nanocoulomb. The charge stored in the combination of C23, that is Q23 is equal Q23 is also equal to what? 10 nanocoulombs. Okay, so that the total charge stored in the combination of Q1, C1 and C23 is equal to 20 nanocoulombs here. Okay, now we have got what is voltage across C1, what is voltage across C23, and what is voltage across C4 already we have calculated, Q also we have calculated. Okay, now let us go back here. Here this is C23, this effective capacitance is combination of C2 and C3. Okay, here the voltage is equal to 100 volt, here the voltage is equal to 100 volt. Hence in the parallel combination also the effective voltage will be equal to what? 100 volt here. Okay, so between these two, here I have C2 and C3. Between these two terminals I will have the voltage of 100 volts. And when we look at the combination of C23, the voltage across the combination of C23 is equal to 100 volt. Okay, and the charge stored in the combination of C2 and C3 is equal to what? 10 nanocoulomb. Now look at this combination of C2 and C3. They are connected in a series combination, and in series combination the charge stored in each capacitor will be same as the charge stored in the combination. So whatever this 10 nanocoulomb is there, same charge gets stored in C2 as well as the same charge gets stored in C3 also. So I can write Q2 is equal to what? That is again equal to 10 nanocoulombs. Okay, and Q3 is also equal to what? Q3 is also equal to 10 nanocoulomb, because both are connected in series. Okay, so even though the charge remains the same, the voltage gets divided here. Yes, and you can observe here the charge is same, both charges are same here, and we can observe the capacitance values are also same. So the voltage gets equally distributed, or I can directly calculate by using the voltage. Consider capacitor C2 here. I can write Q2 is equal to what? C2 into V2. By this I can write V2 is equal to Q2 divided by C2, that is equal to Q2 is equal to what? 10 nanocoulomb here, that is 10 into 10 to the power of minus 9 divided by what is capacitance of that capacitor? That is 200 picofarad. Yes, 200 into 10 to the power of minus 12. And by simplifying this I get V2 is equal to 50 volt. Okay, out of 100 volt, 50 volt is dropped across a capacitor C2. So the voltage across C3 will be equal to what? That is V3. V3 is equal to 100 minus of 50. That is also equal to what? 50 volt. Okay, so this is the value of V2 and V3. V4 already we have calculated. Yes, V1 also we have calculated. We have calculated all the values of charges and potential drops across each capacitor. Here V2 is equal to 50 volt. Here V3 is also equal to what? 50 volt. Okay, this is one of regularly asked questions. You can take the screenshot of this.